We'll see.
We'll see.
Okay, I got the green light to go. So hello, everybody. Thank you so much for joining us today for this SEDS Online webinar. We're really happy that you are with us. Today, we have a really exciting talk, so I'm glad that you're going to be able to experience it as well. Before we get started, I want to thank our sponsor, IAS, for their sponsorship, which really allows us to have all of the resources free of charge. That includes everything on the website, the recorded lectures, learning tools, virtual field trips. You got it. Make sure and check that out online. Today's lecture is by Dr. Adrian Immenhauser, who's a professor and chair for sediment and isotope geology at the Ruhr University Bochum. In 2020, he also became the scientific manager at the Center of Competence for Geothermal Geology at the Fraunhofer Institute, also in Bochum. Adrian received his diploma and his master's from the University of Bern before moving on to Amsterdam for a postdoc and then an assistant professorship at the Ruhr University. And Adrian has a really impressive publication record. I just found out how impressive that was yesterday when I was looking things up, but quite extensive work. And his research is focusing on carbonate sedimentology and spans from modern systems all the way into deep time, uses tons of different types of disciplines from petrography to geochemistry. So really going to be quite an interesting talk. And he's also the past president of our sponsor, IAS. So we're really happy to have him on today. And Adrian, I will give you the mic.
Thank you, Chelsea. Hello, everybody. I hope you can hear me. Otherwise, please let me know. So some time ago, Stephen Loki asked me to give a presentation. And he said, "Lal, just use one of your old talks." But I thought, no, that's not good enough for the SEDS Online webinar. And in order to honor all this hard work that the organizers set in that, I came up with a new presentation, which I call a curiosity-driven journey from caves to the burial domain. And now my presentation is not moving. It's frozen, Chelsea. I have to go.
Try clicking with your mouse. Yeah, maybe go. There we go.
To restart again.
Perfect.
So, as everybody about worldwide, I was grounded for the last 2 years because of a global pandemic. So rather than going to exciting places in South America or Oman or God knows where, I started looking at carbonates at my doorstep. And I figured out that there is quite a lot to get actually. Just two pictures. One is a quarry showing Devonian limestones, and it's a drone image. As you can see, the arrow points to some people for scale. And these are large-scale risk and trust faults that go through these carbonates, sort of resulting in very complicated diagenetic patterns. And the other thing is caves. I didn't actually realize that for a long time, but North Rhine-Westphalia, where I'm actually working, is really a cave country and all the cave decorations. So based on that, I'm going to show you a talk that includes both cave sediments and precipitates from the burial diagenetic domain. I think I've never seen a talk combining the two, so I thought that maybe is something of interest to you. So this is the agenda of today. The overall theme would be carbonates, petrography, diagenesis, geochemistry experiments. And particularly, I would like to show you that, that even as a skilled field geologist, we sort of occasionally reach the limits of what we can do in the field. And here experimental work comes into the game. And I think if the field geologist does experimental work and tries to learn something about the processes in nature, that is beneficial by showing you examples. So we have three topics: a natural carbonate archive that I sort of started looking at quite recently. It's cool carbonates. They're called gravity-defying speleothems, and you will see them in a minute. Topic 2, also a bit fancy, are cryocalcites, calcites that form during glacial, interglacial periods. And then back to a super classical topic, saddle dolomites, and also here experimental work. So obviously I'm I'm merely the spider in the middle of the web. So without a lot of people who have contributed and helped and did this research and stood in the lab, I could not present these data. Topic 1, Natural Archives, Gravity-defying speleothems. They are referred to as helictite, eccentrics, erratics, and so on and so forth, and they're contorted cave carbonates twisting in any direction and protruding out, up and down from cave floor, wall, ceiling, and parent stalactite. I'm going to take the laser pointer. Okay, so we have an image of the ceiling of a cave. You see the conventional sawdust straws hanging from the ceiling, and then you have this, with the yellow arrows, you have this weird little things that protrude from their sides. These are calcitic helictites, but I can offer you something a bit more exciting, perhaps. These are aragonitic ones. These are recent discoveries in a cave that has been found only last year, and these are really among the largest known in Europe. This one is about 1.40 meters across, and you really wonder when you see something like that, how on earth are you going to precipitate something in an abiotic setting? What is here? Okay, that is very spectacular stuff, and there's plenty of TV coverage now in the news and so on and so forth. So, but let's approach the issue from the tools we have as sedimentologists, as petrologists and geochemists. And we start with the calcitic helictites. So the image on the left shows a high resolution image of one of the tips of these calcitic helictites, and then you see the arrow pointing to this zone here. That is called the essential channel or capillary. And up here you have an image, broken example, you see this capillary, and that's a close-up of the surface. So these guys form fundamentally different from conventional speleothems that are formed from dripping and flowing water. Different in the sense that the water is not running across the surface, but is flowing through this central capillary. And these are a series of SEM images. And you see that I'm just enlarging each picture from A to B. So that is again a calcitic helictite, and that the small thing in the middle is this capillary, enlarged, enlarged, and indeed enlarged again. So I don't know how you feel about that, but I see precipitation and dissolution, I see corrosion features, etc., but it is kept open apparently through whatever mechanisms, capillary flow, and apparently it, so is the theory at least, apparently it transports the water even against gravity to the tip of the helictite where it forms new calcite. So from the viewpoint of the carbonate petrologist or crystallographer, we do what sedimentologists do. We make thin sections. So that is an equatorial cut, and you see the central channel, the capillary here, and you see there is this strange dark stuff that shows you that there is something like disequilibrium precipitation. That's a longitudinal thin section. You see that the calcites forming this helictite, they are just blocky coarse calcites, nothing special. That is a portion of the central channel. But if we zoom in this part and then go down here, that is an electron backscattered diffraction image. That is a tool that is often used by structural geologists, and it measures the crystal axis orientation, the Z-axis, and it color codes it. So what you essentially see, the portion of this blocky calcite up here, if you zoom in and measure it, analyze it with EBSD, you see that it is in fact composed of subcrystals, so-called mesocrystals that make this array. That is also on the left side, that is rather complicated stuff, and it usually points to disequilibrium fabrics. So the first message we have here, these are complicated things. These are my favorite ones. These are the aragonitic helictites, and I don't know how you feel. Our world is such a mess presently. I'm really happy to study something that I consider is beautiful, and I think these are just beautiful. So that is an aragonitic helictite tip, and this is a close-up image. You see almost translucent glass-like aragonite crystals, and here you really see why they're called helictites from the word helix or erratics. These are very, very complicated, very strange features. So, chaotic. Chaos theory states that when the apparent randomness of chaotic complex systems, and that is a complex system, there are still underlying patterns. There is intercorrectedness, there is constant feedback law, repetition, self-similarity, and so on and so on. Let's see. So that is something that Chelsea is very familiar with. I'm comparing the helictites from this cave in Germany. Okay, sorry. I'm comparing the helictite from this cave in Germany here, close up SEM, with concretionary carbonates in the lagoon of Abu Dhabi. And I would admit it's not identical, but there is very clear similarities. Again, concretionary carbonates of the lagoon of Abu Dhabi, subrecent, and helictites. So you might ask yourself, what is the relation of a cave in Germany and an aragonitic concretionary carbonates in the lagoon of Abu Dhabi? The honest answer is I don't know, maybe the fluid magnesium ratio, but this is certainly not the standard aragonite mineral that we know from the literature. So maybe self-similarity is something we should look into, underlying patterns in carbonate precipitation and diagenetic environments. So we applied microtomography imaging. So that's the same little piece of helictite. And in red, you see the central channel. And you see that's branching out first order channels to second order channels to third order channels, which do not reach the surface, but they induce protrusions on the surface. And that tells us something that, again, that is a pretty complicated system. So what you usually do is you collect your data and you read everything that has been written about these things. And you can imagine that a lot of people have postulated theories about the nature of these gravity-defying contorted features. And let's just go through the range of interpretations. So some people said the clogging is a mechanism. So for instance, clay minerals that just clog the central capillary, and then the fluid must find a new way. That is not what we observe here. Some people, particularly from a cave in France, have said microbially induced carbonates, and maybe the microbial communities, they have an evolutionary advantage or an advantage if they colonize one part of the tip of the helictite, but not another, and then they have to move to be not entombed, etc., etc. We're not sure of what the role of microbial consortia is here, but certainly we don't see major microbial biofilms on these speleothems. Some people have said, well, airflow affects the growth direction, but that's not the case here. You can do a statistic analysis of the orientation in these caves, and you check the annual airflow direction, and they're against width or an angle to it, so not the case. Something we found, and I remind you of these very complicated surfaces of these particularly aragonitic helictites, something we found is that some people talk about sector growth. That means a little bit of water reaches the surface, the tip of the helictite, And then it has to find its way through this meshwork of arachnoid crystals. And it just randomly moves to one place where it induces precipitation. And that can lead to this very chaotic change in direction. So I think that is probably something that is in agreement with our data. And then I remind you of the microtomography, this very complex internal structure of these capillaries that do not reach the surface or bifurcate and so on. So I think that is also something that should be considered. Okay, but time is running. We have to move on. I would like to go to topic number 2. These are these cryocalcites. And again, my personal opinion is they are beautiful. Okay, so cryocalcite, and we're now talking about the PhD project of Osioma, a student here at Bochum. They are carbonate minerals and mineral aggregates that precipitate from freezing water in ice ponds in caves during glacial and interglacial cycles. That are just a couple of images of naturally formed cryocalcites, and they're very small. You see there's like millimeter or two, some of them are 3 millimeters, and you really have to have a good eye because they're just little grains distributed on the floor of the cave. So you need to be sure you know what you're looking for. And they have attracted the interest of particularly climate researchers, because people argued if we find these cryocalcites, we can date them, we can say something about permafrost depth and glacial interglacial cycles. The problem is you cannot turn time back. So what you find are the precipitates, but you know little about the ice volumes from which they formed. And there have been a series of models and hypotheses, what makes which crystallographic shape and what can we learn. So we've looked at these features. So this is in the upper left, that's a CL image. And you saw these highly complex zonation features. You see these cracks and so on and so forth. And then you see a couple of thin section images here on the lower 2 images with this complicated internal structure. So these are clearly non-equilibrium fabrics, crystallographically very, very, very complicated despite their small size. So here is the one of the models that explains how these features form. So what you have to do is you have to watch this diagram in the lower left and the diagrams up here. And you see it is sort of cold, glacial, warm, interglacial. It is old to young in this direction. And we start with this setting. So we're in the midst of a cold period. And on this diagram, you see that all of the cave is frozen. And there is only a very thin layer where the soil sort of goes above 0 degree during summer months. But with time, we move into interglacial, and this isotherm, this 0 degree isotherm moves down into the soil and reaches the roof of the cave, which means now drip water reaches the top of the cave and is falling down in this natural refrigerator where it forms ice. And that goes on. The isotherm reaches the ice that is now covering the floor of the cave, and meltwater forms, meltwater pools on the ice. Okay. Now, when we go back into the cold stage, isotherm moves up again, and the meltwater on the ice starts to freeze. Okay. And when you freeze the water, the ice is essentially ionized water. You increase the alkalinity of the remaining water in the pond, and you induce precipitation of cryocalcites. Okay, that would be this stage. And then the last stage, warm period. Okay, all the ice is gone, but you find the cryocalcites lying on the floor of the cave. Okay, that's what we have in the field, but we have very little information about the stages before that. So here comes the experimental approach. Why not make our own cryocalcites? Okay, and that sounds easy. It's not that trivial. You cannot just put water in the deep freezer and let it freeze. That is not going to work. We need to control something that is in the range of +1, +2 degree and about -2 degrees Celsius. That's the range where these cryocalcites form. And what you essentially see here is the experimental setup. So there's a water tank in here. There is a stirring device that makes sure that you have no temperature gradient in the water, because otherwise your stirring device will be blocked by the ice. You have watch glasses that collect material that rains down from the water column, and you control the temperature very accurately. So we add calcium and carbonate to the solution, so that we will produce 100 milligram of cryocalcite. And it works. Okay, after some try and error, it works. These are, may I proudly present you the first artificially produced cryocalcites in science. Okay, so it's very small again. You see the dimensions, 20 micrometers, but you have very specific crystal morphologies. You have these round sphere-like objects down here. These are rafts. So they form on the surface of the freezing water, and when they get heavier, they sink to the floor. And these guys here, they form in the water column or on the floor. And the temperature is between +1 and -2 degrees Celsius. These are the SEM images, and they show you quite a lot of diversity, also very strange features. I point your attention to this guy here. Why would they have such features? It almost looks like somebody has been taking out pieces and bits, but that's the precipitate. Okay. So we see a lot of rhomboedral calcite and more complicated features. So when I call them rhomboedral, it's just a descriptive term. And you see these round features. And we realize they form in this upper, so to speak, upper temperature limits of +1 to -2 degree. If we go down to the temperature, so to -2 degrees, 0 to -2 degree, we form these ferrolytic rafts. And when we try to analyze them with EBSD, we failed. So we believe they're potentially amorphous. And that would make sense because amorphous carbonates usually form these spheres. And you see all sort of complexity. Look at this one up here. It looks like an onion with several layers, or this here down here, a close-up of one of the rafts here on this side. So whatever goes on in this freezing water, it is not trivial. So Osioma is collecting a lot of data. That's work in progress. I have to emphasize that. And she's sort of compiling the first diagrams. And just the diagram on the left shows you the pH versus duration of the experiment. And you see that we have samples forming at -2. And you see they form quite rapidly, about after 10 days of the experiment. It takes more time if you freeze the water less rapidly. It makes sense, obviously, and the longest duration is at the highest temperatures. And we also see that here we mainly have these rhomboedral faces that I did show you, and here mainly the spherical ones. These are intermediate, they show both features. This is conductivity versus duration. That shows you that we just, with time, with experimental duration, we use up the calcium and the carbonate in the solution to precipitate these features. Okay, so it is quite successful. And we can now also take these samples and analyze the isotope values, and we see a trend to less negative carbon. It's very negative still, but less negative carbon. and more positive and more negative oxygen isotopes in this direction. And that is nicely confirming work by previous colleagues based on natural cryocalcites. They predicted that this must be the succession. But I believe this is a nice example where we can show that experimental work can just close the gap between what we see in the field and how we interpret that. So what can we learn from these observations combined with published evidence? So where are we? We're in caves. When changed from glacial to interstadial, we can date these samples with uranium thorium. How do we make them? We freeze water in caves on or below ice, so there's degassing and there's plenty of gas bubbles captured in the ice. Degassing and fluid supersaturation drives the precipitation of these features. What do we see in the experiments? What can we learn that goes beyond what we see in the field? So we have rafts. So we have these crystals floating on the surface. We have precipitates on the floor of the experimental setup and such that form in a water column and sink down with time. And we realize that there are in fact subtle differences in the temperature. It's not dramatic from +1 to -2 degrees. It's only a few degrees, but it changes the system from a rhomboidal to a spherical to a properly amorphous precipitation system. And we can now play with pH, conductivity, rate of freezing, degree of supersaturation, and so on to work out the subtleties. And we always need to go back, I emphasize that we need to go back and check with the natural precipitate to see if we do something that has significance for natural system. I'm not interested in producing laboratory experiments that have no connection to nature. Okay, third and last topic, totally different world. Now we are in the burial domain, a very classical topic, saddle dolomite. Nearly every carbonate sedimentologist has seen saddle dolomites. They have their characteristically bent crystal surfaces, and they're also called baroque and pearl dolomite, and there's like a whole literature on it. And they're commonly considered as cements, in other words, precipitates filling open pores, but there is also evidence of replacing saddle dolomites. And all we know is, in fact, is they are precipitated from elevated temperatures, and that could be more than 60, but it could be up to 300 degrees Celsius. That's based on clumped and fluid inclusion temperatures and other temperature proxies. So that's a postdoc project by Ifan. She prefers to be called Eva, which is apparently close to the way this is pronounced in Chinese. So that is first, that's a natural saddle dolomite from the Alps. And that's element map. And you see once more complicated stuff, complicated elemental zoning. And you see there's this green surface outer part, and that's already alteration. So there were like iron-rich fluids going through the system, affecting the dolomite. But I guess everybody sees that the crystal boundaries here are not straight, but warped to some degrees. Okay. So pile of literature on why the crystal surfaces are not flat but warped, and it's not only dolomites, it's also other minerals that show this feature, and people speculate and so on and so forth. Again, here we come. Let's try an experiment. Let's try to experimentally produce saddle dolomites. And again, it's not a particularly complicated setup we use. It's not trivial either, but we have this overall procedure. So we create a solution, which is of course supersaturated with respect to magnesium. We add seed crystals, which are partly dissolved during the experiments, partly serve as a nucleation base on which these precipitated hopefully saddle dolomite should form. We put everything in this liner, close it, put it in a steel cylinder. Keep in mind, if we heat it, there is a lot of hydrostatic pressure building up. So we want to ensure that the thing is not exploding, and then put it in an oven for several days to several weeks at a given temperature here, 220 degrees Celsius. So that is what EVA produces, at least some of the data, SEM images. The good news is these are clearly bent, warped crystal surfaces. There is no doubt here. Now the complexity starts. These are not stoichiometric ideal dolomites with a magnesium to calcium ratio of 1:1. Some of these are non-stoichiometric calcium-rich dolomites. Some of these are highest magnesium calcite, so they have the crystallographic structure of a calcite, but the stoichiometry of a dolomite. So all this complexity that is now a main topic in dolomite research, and where a lot of reviewed papers and so on are published right now, it is visible here in these experiments. Okay, some of them are real dolomites, some of them are magnesium calcium carbonates, but positive warped crystal surface, and that's some close-up images. Okay. Now, the question is, we still do not really know what causes, what induces the warped surfaces, because we find saddle dolomites with the perfect stoichiometry, 1:1. We find saddle dolomites with a non-perfect stoichiometry in nature. We find it as well here. So we are now adding more elements with large ionic radii, such as strontium, for instance, and barium, to these experiments to see what's actually happening. And here is a graph just showing some of these data. We use the Kaczmarek and Thornton graph as an underlying diagram. And you see this blue, yellow, and sort of purple, reddish symbols are our precipitates. You see up here, for instance, so let me explain the diagram first. So that's reaction progress. You could equal it to time, but it's not precisely the same as time. It's progress in this direction. And this is how much product we make, higher temperatures in this direction. Okay. So at the beginning, we precipitate something that is magnesium calcite and has no warped crystal surfaces. We go up with temperature, we go up with magnesium calcium ratios, and we come up to something like this. And this is where the first non-stoichiometric dolomites form, some of which have warped crystal surfaces, but they are non-perfect. You see the magnesium calcium ratio is less than 1:1. And finally up here, this is where we would like to go. These are perfect dolomites stoichiometrically, and some of these show warped surfaces. But then this guy here, again, a non-perfect stoichiometry, and in part warped surfaces, in part not. So if I'm very honest, up to now, we don't understand what's going on, and we do more experiments, and it's really it's like a good example why dolomites still attract the attention of the community after such a long time. They're really complicated. So I have some take-home messages, because I think I'm running out of time. So I'm a field geologist. I think this is where our strength and our foundations must be. And I will never ever want to be a purely experimental sedimentologist. But in some, or you could say many cases, we may have reached the limitations of what we can learn from natural carbonate archives, or say, be specific about their origin and alteration pathway. So in order to advance in our discipline, I propose that solid, very detailed field work and experimental work combined with state-of-the-art analytical tools can be very helpful. And these approaches trigger new questions that in turns asks and makes us ask these questions back to nature. So I see this as a circle: experiment, natural observation, experiment, natural observation, and so on. So the experiment work shown here is neither very expensive nor very sophisticated. You don't need a synchrotron in Grenoble or the like. You need ovens, water, freezing devices, baths, etc. What you need to know is how nature works, and there's, I think, that the messages from the field geologists come back. We don't want to produce something with fluids that are totally out of range of natural fluids. We want to stay close to natural settings. And you should have a conceptual background in carbonate mineralogy, petrology, crystallography, and geochemistry. Thank you very much.
Super. Thank you so much, Adrian, for that wonderful presentation. I was definitely intrigued the entire time. I hope you were in the audience as well. So the chat is now open for any questions that you have for Adrian. Please type in not only the question, but let us know where you're coming from so that we can, just know where everyone's sitting around the world. I will get us started with questions. I have, of course, a few, and then we will get to the ones in the chat afterwards. So one of my questions was for the first set of experiments. So the helictites. I'm just wondering if in the natural system, has anybody actually measured the fluid chemistry?
So I'm going to the helictites.
Yep.
Yeah, we didn't do experiments, Chelsea. That's a good point, because the amount of water, you remember okay, look at that, 50 to 100 micrometers. So the volume, the amount of water circulating through such a small capillary, this is the problem. You cannot collect drip water or flowing water. But we noted that these features, particularly the aragonitic ones, they line up at the ceiling of the cave wherever we have these Variscan fault zones with the intense dolomitization. So I predict that the magnesium to calcium ratio of these fluids that seep through the fault zones will pick up the higher magnesium to calcium ratios of the dolomites, and then force the precipitation of aragonite in a cave that is otherwise calcitic. Okay, but no, we haven't managed to collect these waters so far. That's one of the major issues, actually.
Yeah, that would be interesting to do. Would it be possible with like a crushing device, getting just enough to run ICP or?
Yeah, I mean, that's something I had in mind. If you look at these guys, there must be plenty of fluid inclusion. So the crush leach device, in the sense of what Hubert von Hoff does, etc.
Yeah.
That would be the next step. Yeah, that's actually the only way I see how we could collect these fluids.
Right. And I guess the fluid inclusions might be a little bit different than some of the fluids that are precipitating them, because that's sort of what's left over. But that would definitely be a really nice addition to that project.
Yeah, it's actually something we have in plan but not done so far.
Okay, awesome. And then what about preservation potential of these helictites? Do we have any idea of how that's?
Yeah, let me go back to those here. Okay, so the very white ones, that we have dated them with uranium, thorium. They are something like up to 4,000 sometimes years. So they are like actively forming now. And then you don't see it on this image on the ground. You have brownish, weathered, slightly corroded things. They are 400,000 years old. So for somebody working in the Paleozoic, that's peanuts. But I'm still impressed that apparently we're looking at a system that is active since at least 400,000 years here.
Yeah. And do they look structurally? Do they look very different in comparison to the ones that are forming?
No, they look there's a very conservative system. It's just that they are coated by clay and things like that, and the surface is slightly corroded. But they're still aragonitic.
Very interesting. Okay, and then I had a couple questions about the cryocalcites.
Where should I go?
Maybe continue a little bit more. Sure, how about here? This is a nice one for everyone to sort of look at. Okay, so I'm curious, obviously you were mentioning that the different morphologies are growing in different locations in the water bath. Do we know, are they primarily growing outward? Are they also growing up? And if they are growing up, how thick would those deposits actually get?
So what you find in natural system are really like individual. Let me go back. Where are they here? Individual crystals. You see, some of these are aggregates. So there's several subcrystals, like the one up here, or this guy here. Okay, this guy here. But they're not making like layers of calcite on the floor or something like that. Okay.
And so the rafts that you were talking about that grow sort of at the surface, that's not as typical for natural systems, or?
Yeah, you have them. So this guy here, I don't know if you can see my laser pointer. This guy is a raft. Okay. You see the very flat surface. This is the upper surface where it reaches the water surface, and it hangs sort of underneath the water surface and grows downward. And when it gets too heavy, it just sinks to the floor. And something like the big guy in the middle that would form on the floor of this ice pond.
Okay, so there is a bit of topography then to the ones that grow on the floor.
Yeah.
I mean, not huge.
Yeah, I mean, actually, in the experiment, we really have some that collect on this watch glass. That essentially means they have been falling down through the water column onto the watch glass. Okay, whereas others are really scraped from the side walls of the beaker. Okay, they form there. And it also depends. Do you switch your stir on or off? If you switch it off, you have the usual temperature gradient with ice forming up here and warmer waters down there. And also, if you, depending on where you bring the cold water in, and if you switch the stir up, you have actually also ice forming from the base up, which is also interesting because then you mimic something like a pond on an ice body sort of. If you seal the surface off with the ice layer, okay, the system cannot easily degas anymore, but there is plenty of gas bubbles trapped in the ice that tells you, yes, it is still degassing, but it's just not going to the atmosphere. It's trapped in the ice.
Okay, great. All right, well, we have some questions in the chat that I should get to, so I'll get on to the first one from Teresa, watching from Vienna. Thank you for this great presentation. Do you plan to include water energy or stirring into the precipitation experiments? It seems to make a difference for aragonite precipitation. So I guess we just got a little bit into that for these cryocalcites.
Yeah, Teresa, I presume you refer to the cryos. So in the natural setting in the cave, there would be zero. There would be convection, very limited convection in the water body due to temperature differences, but there would be no flow or something like that. So we're not talking about a river in a cave which is actually flowing. We're talking about a stagnant water body. So the stirring system here comes in to make sure that the fluid is homogenized and to make sure that the thing is not freezing in an uncontrolled manner. But that's really an artifact. We have some experiments that sort of were accidents, which actually very nice accidents. So we froze down the system too quickly, and the stir was trapped in the ice. And it made some of these very nice here spherolytic features, so which are probably amorphous. Okay, So sometimes the experiment does not run according to expectation, but the outcome is still very nice.
She mentioned different water energy. So I guess that you still answered her question. Okay, our next question is from JB, coming from Sorbonne University in Paris. It says, hi, Adrian, having a fluid circulating in the system might change the crystal growth dynamic regarding those dolomites, since the reaction zones around the crystals would be less charged with the available ions in the solution. Do you know if this could affect the stoichiometry? Good question.
Very good question. I don't know. So you certainly will have circulation in this steel cylinder, but that's the limitation of the experiment. I mean, let us think for a moment about the natural systems in which saddle dolomites form. So somewhere deep down, hundreds, thousands of meters in pore space. So there must be fluid circulation, otherwise you wouldn't have the precipitation, but the fluid circulation would be very, very slow. So we're really talking like centimeters per year or something like that, unless you're in a big fault zone or fracture zone. Okay. And with time, so when you sort of precipitate these saddle dolomites, you're just sort of closing the pathways for fluid circulation, and in the end you really have only fluid films on the surface. So complicated, but I agree with you that may affect it, but it's just not what the experiment does here.
Sure. That would be a long postdoc or PhD project if you try to emanate that. So, all right, our next question comes from Noor from Hungary. Thank you for the informative presentation. My question is, what do you think the missing factor that makes dolomite production in the lab still ambiguous?
Well, I mean, there's now, as you know, there's now, I don't know, 25, 50 papers of people who have produced dolomite in the lab, and they're just cheating a little bit in the sense that they go up with temperature, or they add organic compounds or things like that. I mean, what is not working is to precipitate the dolomites under Earth surface conditions. There's this famous paper where somebody has tried it to precipitate dolomite for 30 years in a super saturated fluid, and he failed. Okay, so the really interesting question is these early diagenetic dolomites that we find in marine settings, where apparently under near Earth surface conditions, dolomite replaces calcite or aragonite in carbonate platforms. Take the famous Precambrian dolomitized platforms or the Triassic case examples in the Alps and so on and so forth. So what's going on there? Why do we induce dolomitization under these conditions? I think that's something people are very interested in, and that's very difficult to reproduce in the lab.
So we'll still all keep searching for that missing factor then, Noor. All right, our next question is from Ross, coming from Queen's University in Canada. It says, thank you for this. What a beautiful and intriguing crystals. Might the cryocalcites and helictites ever be preserved in older sediments?
Yeah, I ask myself, I mean, I actually don't know what the oldest recorded helictites are in the literature. I know that people have gone into caves and they found arguments that these were like speleothems from the Cretaceous, okay? And the oldest, latest speleothem as such is from the Devonian. These are pretty small things, okay? And I don't know what the preservation potential, certainly of the aragonitic feature would be. I guess it's not impossible if you seal, particularly in a desert climate, if you seal off your cave and there is very limited water, why shouldn't you preserve a helictite for millions of years? Okay. Now the spherulites, the issue is they form during the glacial, interglacial periods, and if in the post-glacial phase the cave is flushed by rivers, for instance, or sediment is brought into the system, you're just going to bury these things. So I think that's more of a preservation problem than the fact that they would not survive millions of years. Okay, and once they are lithified within a cave soil, it would be very, very difficult to extract them.
Sure. Yeah, I think also finding these things in a natural system might be difficult as well, as you mentioned, just they're due to their size, so tiny. Okay, well, unless we have any more questions in the chat, Adrian, thank you again so much for the presentation. We really enjoyed having you on today. Everybody else, come back in 2 weeks. So now we're in our sort of summer term, so we'll be having our webinars every 2 weeks. So make sure and check our website so that you know when the presentations are going to be and who's giving them. In 2 weeks, we'll have Yarang Sung. We'll be talking about ocean chemistry following the Permian mass extinction, and we will see you then.